This power density video is focused on thermal enhancements possible at the system level, as well as some of the innovations at a package level that TI is developing for its products. Let's first discuss the thermal problem of electronics. Most electronic systems have printed circuit boards with various components that dissipate power under different operating conditions. A system encloses these PCBs along with other components and interacts with ambient, which is most often the air surrounding the system. Power dissipation from components within the system causes their temperature to rise. The temperature rise must be maintained at acceptable levels for the safety of systems as well as the user. Let's take a look at what determines this temperature rise. Materials within the package, PCB, and system give resistance for heat transfer, similar in principle to an electrical resistance. Temperature rise is proportional to the dissipated power and also depends on the effective resistance of all these thermal oppositions in series and parallel. Thermal resistance improvements are hence possible at all levels. We all benefit from shrinking systems and components, but that leads to higher power density and therefore higher temperatures. In addition to improving thermal resistances, if we can develop more efficient components and systems, power dissipation can be reduced, which can directly result in lower temperatures. So what are some of the improvements possible at the PCB and system level? Imagine a quad flat no-lead or QFN package with an exposed pad connected to the PCB. In a typical scenario, more than 90% of power is conducted from the package through the PCB to ambient. Starting from a baseline design, a larger PCB size reduces temperature due to larger area for heat transfer to ambient air. Conducting layers within the PCB helps spread the heat laterally, so adding more layers can also help. If more layers are not possible, making some of the planes thicker can improve performance. Additionally, PCB vias play a critical role in reducing interplane resistance, so adding thermal vias at strategic locations can help further. When there are multiple high-power dissipating components next to each other, it is prudent to optimize their spacing for lowest temperature rise. Besides PCB improvements, other thermal management techniques are possible at the system level. A common technique to manage temperature rise is to use a heat sink attached to a component on the top side. Heat sinks are made of high conductivity materials with significantly larger surface area for enhanced heat transfer with surrounding air. This particular configuration is most beneficial if the internal thermal resistance of the package from silicon to the top is very low. If the thermal resistance from silicon to the bottom of the PCB is much lower, a heatsink on the back of the PCB may be a better option depending on system constraints. One must ensure that there are sufficient thermal vias in the PCB for efficient thermal conduction from package to the back of the PCB. Other techniques in thermal management include using low-resistance thermal interface materials between two mating surfaces, applying gap filler pads for larger gaps to accommodate mechanical tolerances, using heat pipes to transfer heat from hard-to-reach locations, leveraging fans to create forced convection heat transfer, using cold plates for spreading heat, or even jet cooling for localized temperature reduction. Let's take a look at some of the approaches TI is developing to improve package thermal performance. A QFN with an exposed pad is a popular package from a power density point of view. Typical QFN packages are built using bond wire interconnects between silicon and lead frame, which usually have very high electrical resistance. TI's hot rod interconnect with silicon die flipped directly on a lead frame can dramatically reduce the interconnect parasitics and lower the dissipated power. While hot rod technology can lower power dissipation, it can result in less optimal exposed lead frame patterns when compared to a bond wire QFN with a large exposed pad. A narrow exposed lead frame pattern puts constraints on PCB via placement beneath the package and can therefore increase thermal resistance. TI's enhanced hot rod QFN utilizes low parasitic interconnects on silicon for reduced power dissipation, while still offering a large exposed pad for efficient heat transfer to the PCB through thermal vias. It brings together the best of both package technologies for optimum performance. Wafer chip scale packaging, or WCSP, is an attractive solution in mobile and space-constrained applications. Power is conducted directly from silicon to the PCB through a ball grid array. Let's analyze the basics of thermal conduction. Imagine the case of vertical heat flow through a homogeneous material. One can lower its thermal resistance by making it shorter along the heat flow direction or widening the area through which heat is transferred. In case of horizontal heat flow, similar changes can improve thermal conduction. Furthermore, thermal resistance can be lowered by fundamentally using a higher thermal conductivity material for heat flow in any direction. TI is developing Power CSP technology by applying the fundamentals of thermal conduction to provide an optimum solution. Power CSP solutions can run cooler compared to conventional WCSP designs. While experience can help in designing better products, use of advanced computer simulations for accurate predictions and trade-off analyses can help develop best solutions. TI uses numerical simulations comprehending all three modes of heat transfer, such as thermal conduction, convection, and radiation. In some cases, a coupled electrical and thermal analysis may be necessary to capture complex device behavior. These simulations provide a detailed temperature field within the device, including temperature at silicon and package interconnect level. Such temperature fields help identify opportunities for improvements as well as enable robust designs. As an example, a device can withstand lower load currents for larger pulse durations due to self-heating. With optimized designs, higher currents can be sustained for that same duration. On the path to increased thermal performance, TI offers design tools to help with product selection. These include WebBench Power Designer to design your power supply circuit, and a PCB thermal calculator to understand board area required for high power dissipating components. Visit the link below to learn more about available design and simulation tools. Thank you for your time and for watching this video.